In this module, we are going to look at the values of pH and of Kw, the equilibrium constant associated with the ionization of water. Our objective of this unit is to understand the autoionization of water and to calculate the pH values based on the hydronium ion concentrations. When we look at water, what we see is that water can actually undergo autoionization. Two water molecules can react and produce an H3O plus ion and a hydroxide ion. Notice that this process is at equilibrium, and this equilibrium lies far to the left. We only get a very small amount of the H3O plus ion and the hydroxide ion. We can also show this in a little bit of a shorthand notation by showing a single water molecule going to H plus aqueous and OH minus aqueous. Remember that we can't actually have H plus ions free in solution. If we write H plus, what we really mean is that we have H3O plus present. If we look at some of the properties of water, one thing we notice is that it is amphoteric. This means that it can act as an acid or a base. Just as when we talked about the Bronsted-Lowry definitions of acids and bases, we said whether water acts as an acid or a base depends on the identity of the other reactant. Kw is an equilibrium constant. Specifically, we call it the ion product constant for water. We can also call it a dissociation constant, but regardless of what we call it, it's still an equilibrium constant. The W in the subscript lets us know that this is for water. We can still write an equilibrium expression for this just as we would for any other reaction. So how do we write the equilibrium expression? Well, we have our reaction, and here we're using our shorthand notation, but either one will show us the same thing. We have H2O liquid in equilibrium with H plus and OH minus ions. When I'm writing an equilibrium constant expression, or a law of mass action, I'm writing the concentrations of the products raised to their powers, which we have coefficients of 1 for both H plus and OH minus, so we don't have any powers in the expression. And on the bottom, in the denominator, we put the concentration of our reactants. However, we remember that we exclude both our solids and our pure liquids, so we do not include water in our denominator. So the equilibrium expression, or the ion product expression in this case, is Kw equals H plus times OH minus. Another thing that's important to remember is that the value of Kw. Notice that this is only true at 25 degrees Celsius, that Kw equals 1.0 times 10 to the minus 14th. As we change temperatures, we change the value of K, that equilibrium constant, just as the values of equilibrium constants for other reactions also change when we have a change in temperature. Let's look and see what we can find about the values of the H plus and OH minus concentration for a sample of pure water, given that we know the value of Kw. So if we're at 25 degrees Celsius, our Kw value is 1.0 times 10 to the minus 14th. That equals the H plus concentration times the OH minus concentration. If we're looking at a sample of pure water, our H plus concentration must be equal to our OH minus concentration because of the balanced reaction. And so let's represent them both as x. Therefore, we end up with 1.0 times 10 to the minus 14th equals x squared. When I solve for x, I get 1.0 times 10 to the minus 7th. And that is going to be equal to the concentration of H plus, as well as the concentration of OH minus in a sample of pure water. We're also going to look at later about what happens when we're not at 25 degrees Celsius, when we have a different value of Kw, and what that means for the concentrations of H plus and OH minus, both in pure water, as well as in either an acidic or basic solution. First, let's look at an example of how we find OH minus if we know the H plus concentration. So for example, if we have a solution that has an H plus concentration equal to 3.5 times 10 to the minus 5, we know we're at 25 degrees, so we know that our Kw value is going to be equal to 1.0 times 10 to the minus 14th. We can set up our expression. 1.0 times 10 to the minus 14th equals 3.5 times 10 to the minus 5th. times our hydroxide concentration. That's our unknown that we're trying to find. When I divide both sides by 3.5 times 10 to the minus fifth, I end up with 2.9 times 10 to the minus 10th equals the OH minus concentration. I could do a similar calculation if I knew the OH minus concentration and needed to find the H plus concentration. But at 25 degrees Celsius, this expression will always be true. 1.0 times 10 to the minus 14th equals H plus times the OH minus concentration. Most of the time when we're looking at solutions, we're looking at them at 25 degrees Celsius. And so we most commonly use this kW value, 1.0 times 10 to the minus 14th. However, if we decrease the temperature, we see that the value of kW changes, or if we increase the temperature, we see that the value of kW changes as well. You should know the value at 25 degrees Celsius, but if you're doing calculations at a different temperature, then it's okay to be able to look up these values. Now note that some of these values are not written in the correct format for scientific notation because we wanted to be able to compare the numbers and have the powers be all the same. So when we're at 25 degrees Celsius, if we have a sample of pure water, we know that it has an H plus concentration of 10 to the minus 7th. And what we want to be able to do is find the pH from that. And so we say the pH is equal to the negative log of the H plus concentration. So we can find that the pH of water, when the concentration of H plus is 1 times 10 to the minus 7th, the pH is equal to 7. Okay. Now when the pH is equal to 7, we know that the pOH is also equal to 7, and we can do this two different ways. We can take the pOH equals minus log of OH minus. Remember, if the H plus concentration is equal to 1 times 10 to the minus 7th, that the OH minus concentration is also equal to the 1 times 10 to the minus 7th. So I can take the negative log of 1 times 10 to the minus 7th and find the pOH value is 7 as well. Or we can take advantage of the fact that pH plus pOH equals 14. Now note, this only applies at 25 degrees Celsius because our kW value is equal to 1 times 10 to the minus 14th. If we had a different kW value because we were at a different temperature, then this expression would no longer be true. We would still be able to say pH plus pOH equals something, but we'd have to have a new value instead of 14. Using a pH meter, we can easily measure the pH of a solution. However, that doesn't directly give us the concentration of the H plus ions, but we can use the pH and be able to calculate that H plus ion concentration. This is our expression for finding the pH from our H plus concentration. This is the relationship that we know. pH equals minus log of H plus concentration. Now I'm going to rearrange this to solve for H plus. So I have minus pH. I've divided both sides by -1. So minus pH equals the log of H plus. Now to get rid of the log, I'm going to take 10 to both sides. Remember that 10 and log are opposite functions. In the same way that if I divide by 6 or multiply by 6, they do opposite things to the number. What I can also see is that x equals 10 to the log of x. The log and the 10 cancel each other out and we're left with x. We can take advantage of this by saying 10 to the minus pH equals 10 to the log of H plus, and I can simplify that because those two terms, the effect will cancel each other out, so we end up with 10 to the minus pH equals the H plus ion concentration. So if I'm able to measure the pH of a solution, I can then find the H plus concentration. I could also do the same thing with my pOH. If I had a pOH value, I could find the OH minus concentration. Now we want to look at some examples where we're not at 25 degrees Celsius, where we're at a different temperature, in this case 40 degrees Celsius, and our kW value is 2.92 times 10 to the minus 14th. Now note that this first part is just about looking at the conversion of H plus from the value of the pH that was measured. You should have found that the H plus concentration was 3.98 times 10 to the 5th molar. We can do this by saying 10 to the minus pH equals the H plus concentration. This is the expression we derived from the formula for finding the pH from pH equals negative log of H plus. Here I put in 10 to the minus 4.40 equals my H plus concentration, and I find that that equals to 3.98 times 10 to the minus 5th molar. Now we're going to take this one step further and look at what the OH minus concentration is of this same solution. But we have to remember that we are not, in fact, at 25 degrees Celsius. We have a different value of Kw. So what is the OH minus concentration of a solution with a pH of 4.40? At 40 degrees, note that the Kw value at that temperature is given. Now we can solve for that OH minus concentration. We know that Kw is equal to H plus times the OH minus concentration. We know that Kw is equal to 2.92 times 10 to the minus 14th. And we know from our previous problem that our H plus concentration is 3.98 times 10 to the 5th, negative 5th molar. And so now we can solve for our OH minus concentration, and what we find is that it's 7.5 times 10 to the minus 10th molar. We can go back and check our work by multiplying 3.98 times 10 to the minus 5th times 7.5 times 10 to the minus 10th, and we should get a value somewhere close to the 2.92 times 10 to the minus 14th. However, we have to ask ourselves, why can't we use pH plus POH equals 14? Remember, this is only true at 25 degrees Celsius. This is only true because Kw at 25 is equal to 1.0 times 10 to the minus 14th. Different value of Kw, we cannot say pH plus POH equals 14. Let's look at an example where we look at the OH minus concentration given the H plus concentration. We are at 25 degrees Celsius, so we can remember that Kw equals 1.0 times 10 to the minus 14th. Once we find those two values, we can then find pH and POH. By knowing the H plus concentration, pH equals negative log of H plus, we can find the pH value. For POH, we can do the same thing, 9.54. And what we do notice is that 4.46 plus 9.54 is equal to 14. And this works out because we are at 25 degrees Celsius. When we're looking at calculations involving logs, we have to be careful about our significant figures. Note that this value, the 3.5, has two significant figures. That will be the number of digits in our mantissa, or the number of decimal places in our answer. So we have two sig figs here. We have two decimal places here, but as a result, we end up with 3 sig figs in our answer. So the number of sig figs equals the number of decimal places. In the next module, we'll talk about acid strength and compare strong and weak acids.